Hello my viewers, welcome once more to my channel. In this particular lecture series, we'll be looking at problems involving circuit analysis. In the previous lecture series, we talked about Kirchhoff's laws and how to apply those laws when you're working with complex circuits. So now I have an example here. Where we are going to apply the Kirchhoff's current law and Kirchhoff's voltage law. Looking at the circuits on your screen, we can see we have two loops. We have loop A and we have loop B. Now we are asked to find I1, I2, and I3 using Kirchhoff's laws. Even if you are not told to use Kirchhoff's laws, you know you can use Kirchhoff's laws. So looking at this problem, how do we find I1, I2, and I3? The first step to do is you assign an arbitrary direction of current flow, which I have already done. If you see loop A, I have chosen clockwise direction as the arbitrary direction of current flow. Ignore what you are seeing in I1, I2, I3, just ignore the direction. Choose any direction you want to choose. You can decide to choose an anti-clockwise direction, so it will not be in this pattern, but I have chosen to work with the clockwise direction. So this is loop A. This arrow you see is indicating the arbitrary direction I've chosen for current flow. That's the first step. You do that for loop B also. Then next, you apply Kirchhoff's current law first. Looking at the figure, you have to locate the point in the figure where Kirchhoff's current law can be applied easily. Now remember that law states that the sum of the current entering a junction is equal to the sum of the current leaving the junction. If you check this particular problem, if you check all the points A, B, C, D, E, F, you discover that at point E, you can easily apply that Kirchhoff's law, because if you check point E, current I2 is entering point E, I1 is also entering point E, and I3 is leaving point E. So since we say sum of the current entering a junction is equal to the sum of the current leaving the junction, two of them are entering, which is I1 and I2, and only one is leaving. So we have to equate the sum of I1 and I2 to I3, applying Kirchhoff's current law. So we say that applying Kirchhoff's current law, just simply say KCL for short. So applying KCL, just say applying KCL. KCL implies Kirchhoff's current law at point E. We can say that I1 plus I2 is equal to I3. We can call this one equation 1. Next is to apply Kirchhoff's voltage law, which is KVL, to loops A and B. So for loop A, KVL gives us this. So how do we apply KVL? You have to recall the law. What does KVL state? In simple terms, it states that the sum of the EMFs, that is the electromotive forces, in a closed loop or a closed circuit is equal to 0. So meaning that when you add the EMF of each component in the circuit, it will sum to 0. So if that is the case, let us apply that to loop A first. Now, in applying that, remember what I said initially, you have to assign an arbitrary direction to current flow. So if you check this particular one, loop A, we'll discover that I have chosen the clockwise direction. And so since I have chosen the clockwise direction, there is another step to follow. Now, I'm starting with this cell here. So if I'm coming this way in the clockwise direction, since I have a cell here, the long part is the positive terminal and the short line is the negative terminal. Since my direction of current flow is clockwise, if you check this particular cell, you discover that the current is flowing out from the negative terminal. So the potential drop here is going to be negative. So we say minus 10. We come to this resistor. You see that I1 is flowing through this 5 ohm resistor. It is moving in the opposite direction of this assigned direction we have chosen, this clockwise direction. The current coming through R1, that's 5 ohm resistor, is moving in the opposite direction of this. So we'll have to take the potential drop here to be positive. So if the current in a particular resistor is moving in the opposite direction of the arbitrary direction you have chosen, then the potential drop in that resistor is going to be positive. So we say plus (5I1). You know V is equal to IR. So I1 is current passing through, R is resistor, so IR is V. So say 5I1. On getting to this cell, remember we are still moving towards your left in the clockwise direction. So in getting to this cell, the current is also coming out from the negative terminal. So the potential drop there is negative. So we say minus 6 volts. On getting to this resistor, this is the direction we chose, remember. This time it is now in the same direction as the current flowing through this resistor. So if it's in the same direction as the current flowing through the resistor, then the potential drop is going to be negative. Take note. If they are in the same direction, potential drop is negative. If they are in opposite direction, potential drop is positive. So we say minus 3I2, and all these will sum to 0. So if we rearrange this equation, we are going to obtain, you can ignore this unit 6 volts here, just ignore the unit, okay? So let me just even wipe it off. So just simply say minus 6 minus 3I2. So we rearrange to say 5I1 minus 3I2 minus 10 minus 6 is minus 16 equal to 0. So if we write this again, we have 5I1 minus 3I2 equal to 16. Let's call this one equation 2. Then we go to loop B. Now, one thing you need to know in loop B, that we have worked with 5 ohm in the first loop, will not make us to ignore it in the second loop. It cuts across both loops. So we'll work with loop B separately. So for loop B, KV gives us this. I'm starting from this 5 ohm resistor. Remember, I have chosen a clockwise direction. Sorry, I've chosen a clockwise direction. So it implies that I'm moving this way. And so you see that I1 is in the same direction as this clockwise direction I've chosen. So the potential drop there will be negative. So we say minus 5I1. If we come to this, we're also moving in the same direction as I3, passing through this resistor. So we say minus 4I3. Coming to this cell, since this is our direction, we enter through the negative and come out through the positive. So since the current is coming out through the positive terminal, the potential drop there is positive. So we say plus 6 equal to 0. We can rearrange this to give us minus 5I1 minus 4I3 equal to minus 6. Call this one equation 3. Since they are carrying a negative sign, you can decide to multiply through by minus 1 and make it positive, or go through, just walk through like this. It won't change the answer. However, I'm not going to multiply by minus 1, I'll just walk with this. We're supposed to solve the equations simultaneously. If you check equations 2 and 3, you discover that we have I1 and I2 as the unknown in equation 2. In equation 3, we have I1 and I3 as the unknown. We can't proceed with these equations. But if we recall equation 1, we'll discover that I3 is equivalent to I2 plus I1. So we can substitute that into equation 3. So you can say using equation 1 in 3, so in other words, substitute equation 1 into equation 3. So we say minus 5I1 minus 4 into I3 from equation 1 is I1 plus I2, all equal to minus 6. So if that is the case, let's simplify this bracket. So we have minus 5I1 minus 4I1 minus 4I2 equal to minus 6. So that's minus 9I1 minus 4I2 equal to minus 6. So we call this one equation 4. So looking at equation 4 and equation 2, we can solve them simultaneously since equations 2 and 4 have the same unknown. So let's bring the equations together. This is equation 2, I'm rewriting it. So we have 5I1 minus 3I2 equal to 16. This is equation 2. Remember, I'm writing it again. Then minus 9I1 minus 4I2 equal to minus 6. This is equation 4. So what we are going to do now is to Solve equations 2 and 4 simultaneously. How do we do that? We have to consider using method of elimination. So, which do we eliminate? It's up to you. You can choose to eliminate I1, you can choose to eliminate I2. But me, I'm choosing to eliminate I2. How do I do that? I have 4 here, I have 3 here. What I will do to be able to eliminate I2, I will multiply equation 2 with 4, which is the coefficient of I2. So I'll use this 4 to multiply everything in equation 2. Come to this same equation 2, use 3 to multiply everything in equation 4. Just to eliminate I2. If I choose to eliminate I1, then I'll multiply everything in equation 4 by 5, then everything in equation 2 by 9. Okay, so multiply equation 2 by 4. I'll use short form. This is short form for equation. So multiply equation 2 by 4. And equation 4 by 3. So that will give us, if I multiply the equation 2 by 4, 4 times 5 will give us 20, so have 20 I1 minus 4 times 3 will give us 12 I2 equal to 16 times 4 gives us 64. Call this one equation 5. Then go to equation 4, multiply everything there by 3. So 9 times 3 gives you minus 9 times 3 gives you minus 27 I1 minus 4 times 3 gives us 12 I2 equal to 6 times 3, 18. Call this one equation 6. Now, how do I proceed now? I have minus 12, I have minus 12. The only way I can be able to eliminate I2, since they are not having the same coefficient, but they also have negative number, is to introduce a negative sign here. So I will subtract equation 6 from 5. If I do that, this negative and this negative will amount to plus. So I'll be able to eliminate this part. So I'll say subtract equation 6 from equation 5. If we do that, 20 minus 27 will give us 20 plus 27, which is 47 I1. Minus 12 minus 12 will give us minus 12 plus 12, which is 0. So say plus 0 equal to 64 minus 18 will give us 64 plus 18. That will amount to 82. So we ultimately have that 47 I1 is equal to 82. If that is the case, I1 will be equal to 82 over 47, which yields 1.7447 ampere. this we can actually approximate to 1.75 amperes. So we say I1 is approximately equal to 1.75 ampere. So having obtained the value of I1, we can proceed to obtain the value of I2 and I3 using the equations that we derived initially. So let us recall equation 2. This is equation 2. Since we have gotten the value of I1, we can substitute into equation 2 or any other equation to get the value of I2. So recall equation 2. Now, if you check the problem very well, you discover that when we multiply, we have 8.75 minus 3i2 equal to 16. So that minus 3i2 will be equal to 16 minus 8.75. And that gives us 7.25. So we have 7.25 divided by minus 3 to get I2. So say minus 7.25 divided by 3 will give us minus 2.42 ampere approximately. So having obtained the values of I1 and I2, we can then substitute them into equation 1, which gives us the equation for the current law to be able to calculate the value of I3. So using equation 1, equation 1 tells us that I1, say recall equation 1, so if that is the case, I1 is 1.75 ampere plus I2. I2 is minus 2.42 ampere equal to I3. So we have 1.75 minus 2.42 ampere equal to I3. Therefore, our I3 is equal to minus 0.67 ampere. So our currents, the values for our currents are I1 is equal to 1.75 ampere, I2 is minus 2.42 ampere, and I3 is minus 0.67 ampere. So you see how simple it is to use Kirchhoff's laws to find the values of currents. Once you know the law, know how to apply it, then solving for current become a very simple issue. So this is just one problem. Remember to like my channel. Remember to subscribe to my channel to receive more notifications once new videos are uploaded. Please share my video. You can drop your comments at the comment section. Constructive criticism are very much welcome. Drop your comments and be rest assured that your comment will be handled. Subsequent lecture series, I will also address some more problems on Kirchhoff's laws. Thank you. Have a good time.